So welcome back. We're now at lesson 10B, Is It Getting Crowded? In the last class, we presented a hypothetical example of population growth for rabbits. Now let's use some of those concepts to explore real-world population data. Let's look at the population data and the sources that you collected and analyzed in preview assignment 10B. Compare the data and the sources with, well, you don't have any group members. Probably you're working on this by yourself. So right now would be a good time to just reflect. I would hit pause, look at question 1, and make some answers and thoughts for question 1. And after you do, come back and we'll talk through this a little bit more together. So the questions were which sources would be the most credible, which values are more likely to be accurate, and which values are most likely to be inaccurate and why. Some possible thoughts are that data are less reliable if a lot of estimation is required or if you're extrapolating across a long period of time. A source like the United States Census Bureau is likely to have more reliable to be more reliable than websites by unknown people or unknown groups. So the objectives for this lesson are that you will understand that models are mathematical simplifications of real-world data and phenomena. Different models may be better at matching data than others. More complicated models are introduced to overcome the deficiencies of simpler models. We're also going to be able to evaluate the mathematical appropriateness of a given model given the historical data. We'll also determine whether a data set suggests a linear or an exponential relationship. And finally, we're going to use an appropriate model to predict a future outcome. Now let's examine the world population data from our preview a bit more carefully for signs of linear or exponential growth, and then adjust the exponential model to accommodate patterns in the data that are not reflected by the exponential model. So they're asking us to look at the data of the world population, and we're going to call it P. And remember, I've asked you to do flashcards or a glossary or Google Doc or something. And this needs to be some information you're putting on that list that we're calling the population, the world population, capital P. And your tables of values from question 1 of the previous assignment. Compare the results of your calculations for the first differences. I want you to go ahead and write down for first differences, capital R. And then the average rate of growth with the others. And again, you don't have a group, so we're comparing, but we'll compare with you and me. And on the average rate of growth, I want you to put R for the first differences divided by P, the population. Determine if a linear or an exponential model is going to fit the data best, and how will you know? So now I'm looking at the Excel spreadsheet, and what they're asking us to do in question 2 is to look at this data, look at the population, look at the first differences, look at the average rate of growth, and talk through what you are seeing. And so I'm going to go ahead and look at the first differences. And I've put those way off over here, and I'll end up using them. But looking at the first differences, and I'm going to go ahead and get some borders on here. Looking at the first differences, that's like finding a slope, because I'm taking the y2 minus the y sub 1, and I'm putting it over one time period. And so it's like dividing by 1, or in this case, it would be more like dividing by 10 because of the 10 years. But even so, looking at these numbers, we are not getting the same number. So even though right here on my graph, where I have the year and the population, it appears that it could be linear, but when I go deeper and look at the first differences, it's not looking linear. So that's when we're going to go look at something else. We're going to look at the average rate of growth. And the average rate of growth is we're going to take our R, our first differences, and we're going to divide it by P, the population. And remember, we don't have anything in the first cell, because to do this average rate of growth, I've got to have an ending and a beginning population than to divide by the beginning? Well, this is the very start, so I may have an ending or a beginning, but I don't have both. So that's why I have to start with the 1960 and do the information for 1960 minus 1950, and then divide by 1950, and I get the number you see here. If we want to write it as a percentage, we get this number, the 18.9. So it is probably best to compare with the average rate of growth using these different data points. The first differences are not constant, as we see right here. They're all over the place. But when we look at the average rate of growth, the proportionality ratio, it is close to constant, but probably not close as what you or I would want it to be. One's an 18, one's a 21, a 20, a 15, 12, 10, 8. It's close, but it's not really close. And so the data, they are close to exponential, but it's not looking good. So looking at question 3. Looking at question 3, let me grab question 3. So question 3 says, examine the values of this average rate of growth. If the data represent an exponential relationship, what characteristic do you expect to see in the values of that column, and why do the actual values differ from the expected values? Go ahead and hit pause, write down an answer, and then come back and we'll talk through question 3 together. The expected values should be constant. And the actual values may vary. The actual values may vary because we are using real data and it's often messy. And if you didn't use the same website I used, we could have slightly different data. But one thing we can note in this data set is that the rate of growth was increasing from 1950 to 1960, and again from 1960 to 1970. But then at that point, the rate of growth started decreasing. So going back to look at the Excel spreadsheet, I have taken column B, which is the population, and column D, which is that average rate of growth as a percentage, and I've graphed it. And it depicts what was just mentioned of the average rate of growth going up from 1950 to 1970, and then that average rate of growth decreasing. So even though our population, our P, is going up, the growth of that rate, the growth of that population, the rate of that growth is decreasing. Moving on to question 4, a lot of pieces and parts are missing on mine, so I need to fill it in. And if yours are missing, go ahead and get them before you hit pause. But right here, it says R divided by P. And I'd like to go back, look really quickly at this Excel spreadsheet, and R divided by P is the average rate of growth. So we could say the average rate of growth is a constant times some L minus a P for some unknown values of K and L. And remember, P is population. For some unknown values of K and L. Solve the equation for R. And looking back at the spreadsheet, R represents first differences. There's going to be more discussion about K and L in later discussions, but they're asking us to solve the equation for just R. Do not freak out about this. Look where the R is, and you see the R is in the numerator right here on the left-hand side. And so if we simply multiply both sides by P, then this P divided by P becomes 1, and we're done. The R is worth K times the L minus P times P. We're going to talk more about this later, but just one little step to introduce you and tie in R being first differences, P being population, and them stacked together is the average rate of growth. We're going to move on to question 5. This is a good time to hit pause. Go ahead and put your answers in, and then we'll come back together and talk about question 5. So in question 5, it says complete the table of values and sketch a graph of your formula in question 4, Assume that K is 1/10 and assume that L is 100. So I'm going to go ahead and do 25. You might want to look at that before you hit pause, and then it would be a good time to hit pause and go do the rest of these. So here is a population, and then here is an R. It's first differences, but it's written like this. So on the side, I'm going to start plugging in values to find R. They're asking us to let K be 1/10 and times L. They want it to be 100. P, the one that I'm working with you, is 25. And then times P on the other side. Not on the other side, but in the back side. So order of operations state that we need to do what's inside the parentheses first. So I'm going to subtract this first, and that looks like a subtraction, but it's a multiplication. Both of those are. So either in your mind or on your calculator, let's do 100 minus 75, and we get an answer. And we get 100 minus 25 to get an answer of 75. And I'm going to multiply it times the 25 and times the 0.1. And when I do, I'm going to put my result right here, that it's 187 and 5/10. This is a great time to hit pause and then come back, and I'll have the table filled out with the remaining answers. So I filled in the remaining answers, and something you might observe is we have a 0 at the beginning and a 0 at the end, and then before or after each 0 we have 187.5, and then we have the highest part of 250. It asked us to do two different things. It asked us to sketch a graph, we'll complete the table, and then to sketch a graph. Here's a picture of the graph. Notice that down in the bottom left-hand corner, everything starts at 0, 0. Notice that P is across the bottom, and R is up on the vertical axis. We start at 0, 0, and back over here at 100, we end back at 0. And the comment is that graphs may vary. In other words, whatever you're doing may be different, but that we all should have roughly the same upside down U shape, where R is 0 and P is 0, and then R is 0 at P at two different places. P is 0 and where P is 100. So notice this, that it looks like an upside down U. This is a great time to hit pause again. Look at questions 6 and 7, and then come back and we'll work on these together. Looking at question 6, it says, assuming that the formula used in questions 4 and 5 is correct, then answer the following questions. Part A, what can you say about the population growth when the population is very close to 0? And what would account for this? And sorry about that. What would account for this? And I did it again, so I'm not even going to underline that one. What would account for this? It could be an idea that you think that if the population size were very close to the left edge, then the growth is relatively small due to the limited number of opportunities for breeding. What could you say, or what can you say about the population growth when the population is very close to L? Kind of like the word limit. And what would account for this? It could be that if the population size is very close to the right edge, then the growth is relatively small due to limited resources that are available. We'll be talking about deer on an island, and if the deer population gets too large, then the food resources could run out. And then finally, part C, what can you say about the population growth when the population is very close to the middle of the graph, and what would account for this? Something you might consider for this is that if the population size were in the middle of the graph, then the growth would be large because there is neither limiting constraint affecting the population, being not enough animals to breed or too many animals that they're eating all of their resources. So finishing up this lesson with question 7, it says that the graph you completed in question 5 relates the rate of the growth to the population size. We are interested in determining how population changes over time. So start with a small population at a given time. How will the population change? How will this cause the rate of the population growth to change? Again, if you have not hit pause, go ahead and hit pause, write something down for all 4 parts, and then come back and we'll talk through these together. Something you might consider for part A is that if the population is very, very small, then the population is going to grow very slowly. However, as the population grows, then the growth rate will also increase, and so it will, or it could, snowball. Part B, assume that the population has grown significantly so that it is getting close to size L. And a kind of a word I said a while ago was a limit. How will the population change? And how will this cause the rate of the population growth, the rate, huge concept, of the population growth to change? Well, one thought is if the population is close to L, its growth rate will remain positive, so it's going to keep continuing to grow, but it will grow at a slower rate. And as it grows, its growth rate is going to continue to slow. And think about the population earlier we looked at from 1950 to 1970, how it was growing very quickly. And then the population was still growing, but the growth rate was slowing down every decade. Part C, what is it about the equation that causes this behavior in the growth rate? I want to go back to that equation. So looking back at this equation, let me find a color. Looking back at this equation and then reading question part C, what is it going to be about the equation that causes the behavior in the growth rate? And so right here, L is 100. So I'm going to put 100 right here. And this population, as this population gets closer and closer to 100, then the smaller the difference or the distance between the two is going to become. And what it's asking on part C is what's going to impact the behavior of the growth rate. As P, the population gets closer to this limit, it's going to slow everything down. The closer and closer it gets, it's going to slow it down, it's going to have a smaller difference. And if it were to end up 100, all of this turns out to be 0. And if you're multiplying by 0, then our R is going to be 0 itself. So if you have not already hit pause and you have not already tried all of these parts, part D is one that it would really be valuable for you to spend some time thinking, sketching, trying to get something down for what this might look like. It says, although time increments are not included in the table in question 5, try to create a rough sketch of the population size over time. And keep in mind, we've talked about some slow growth, some fast growth, maybe some more slow growth. So play around with this, and I will give you 2 ideas. Put time, I know you're thinking we always do that, and we do. Put time on the horizontal and put population on the vertical, and just think about what's going to go on over here in this quadrant depicting the growth rate. Here's the sample graph provided in our curriculum. Up here where it says sample answer, the right-hand column of the table indicates that the growth is always positive, but after a period of time, the rate decreases, which means the graph will be increasing everywhere and will look something like an elongated S. Think about this graph where you have time on the horizontal, population on the vertical. And early on, remember when our growth was close to zero on the far left and on the far right, that's going to be your areas of slow growth. So when you see at the bottom, slow growth, and then as we're getting closer to the limit, we have fast growth, but it's been slowing back down. So just a picture to keep in mind, and we'll be looking more in depth at this in future lessons. So this finishes lesson 10B. You need to look at your syllabus to see if we have more lessons that are due for you this week. If we do, keep going and definitely do the homework that goes with the lesson. If we don't have any more homework, then finish this up, and I'll see you again next week.